it's very important to get started with the first talk and talking about some of the fundamentals in federated learning. So my name is Baochun Lee. I'm a professor at the University of Toronto, and it's actually 9 p.m. right now. I'm in Hong Kong. I'm on sabbatical leave from the University of Toronto right now. And today I would like to talk about the applications of deep reinforcement learning in federated learning. This is a joint work with my senior PhD student, Hao Wang, who is graduating this year, and also my Huawei colleagues, Zhenhua Hu and Tim Zell. All right, so now just want to get started with some statistics. So the number of papers that have been published in the area of federated learning had accelerated in its strength and growth over the past several years. Especially if you see the difference between 2018, 2019, it has become an especially hot area of research starting from 2019. 2020, we don't know yet, but most likely it's going to be even more emphasized in the research community. This is mostly because that federated learning is a research area that is between mobile computing and machine learning. So what we wanted to kind of talk about today is some of the challenges and some of the things that we recently have done related to federated learning. And federated learning in general follows the basic guiding principles of edge computing. And it tries to bring code to data rather than bringing data to code. So rather than trying to say, let's upload all of the data to the cloud and try to perform machine learning workloads in the cloud, it tried to say, let's do it as much as possible on the edge devices. So, of course, with mobile devices, you have a large number of these very capable and very powerful hardware sensors and opportunities for collecting data. And with these hardware capabilities, we have an increasing large amount of data that we have collected on these mobile devices. And of course, we can perform machine learning tasks on these the data that we have collected. But the key important problem that we have here is that lots of the data that we have collected on these edge devices, including mobile devices, they are actually private. So you cannot really try to kind of outsource them to the cloud for processing. One very good example here is the Google keyboard. This is some kind of a smart keyboard that you have that when you type something, it will recognize and try to learn from what you have been typing. And this has, as you can see from the short video, already incorporated into the Android platform. Here's another example of a keyboard-related a machine learning task where you can actually try to do some kind of a phrase prediction or next word prediction. Again, this is something that is already incorporated in real-world products. For example, here we have an example of Gmail, where when you type a single letter, it will try to predict the rest of the sentence for you and try to complete that. So the question here is, how do we actually try to make it a little bit more accurate? Now, whatever we're typing into a keyboard or into an email, of course, is extremely private information. It will be way better if we can try to do the learning on the devices rather than in the cloud. So what we have here is that we have these mobile devices and collect data, but we're not only limited to these mobile devices. We can actually have things way beyond mobile devices. For example, we can have institutions such as hospitals that collect private data of patients. We could have devices such as Internet of Things sensors that collect probably privacy-sensitive data from their environments. But today, we would like to take mobile phones as another example and try to say, how do we actually try to do this federated learning using mobile phones? So I thought, because this is the first talk in the morning or here in the evening today, I would like to just want to briefly introduce the federated learning paradigm. So the idea here is that we start from a certain algorithm. And this algorithm, typically at the very first papers, they started from something called federated averaging algorithm. So the federated averaging algorithm is going to be running in something called a federated learning server, typically in the cloud. So the server is going to have an initial model, and that initial model will be kind of disseminated and distributed to all of the mobile devices. And then these initial models will be kind of fine-tuned by using the locally generated data that are private, that you cannot really upload to the cloud, and you can only run machine learning tasks, workloads on the local devices. And after these initial models are fine-tuned, you kind of have better gradients and better models, and you send these gradient updates to the cloud, model parameters to the cloud, and the cloud will update the global model using these parameters. And of course, we don't want to send all of these devices to the cloud. We only want to send some of these devices to the cloud. And how do we actually do the selection? Well, initially, we can actually do something very simple. We can try to do that as random selection. And this is something that we just randomly select the devices and let them upload to the cloud. And once the global model is updated using federated averaging, we are able to just send the actual updated model to the devices in the next round of training. And in this particular idea of federated learning, we have quite a number of challenges. And today we just want to talk about briefly two challenges. The first challenge is communication overhead. And the second challenge is statistical heterogeneity. Now let's start from the first challenge, communication overhead. Now communication overhead is something that is about the amount of work that we try to do sending the model updates to the federated learning server. So it might be hard to imagine, but sometimes sending the actual model updates would actually incur a larger amount of traffic as compared to sending just the raw data to the federated learning server. And the communication in the network is actually slower than local computation. And that is true, and it's by several orders of magnitude. So by combining these two reasons, we would like to be very careful when we're trying to send model updates to the server, because we're sending a lot of data, and sending data is actually quite slow. And because of these reasons, we want to reduce the communication overhead. And there are a lot of papers in the recent years, 2018 and 19, have a lot of potential measures of reducing overhead. For example, we can reduce the number of communication rounds. We can reduce the size of the transmitted data in each round. But today, we just want to briefly talk about one little thing, which is to actually try to run more communication rounds on the local device rather than sending data for every single local batch of updates. So on the local device, before we send data to the federated learning server, we go through multiple mini batches of data. And this is typically called local updating. And of course, the more that we do the local updating, the actual kind of more that we deviate from the global model, and it's not guaranteed to converge. because we're actually not using all of the data across globally across the entire system. But this actually reduces the total number of communication rounds quite dramatically. And with the trade-off that we don't have convergence guarantees, especially with the federated averaging algorithm, which is the initial algorithm that is proposed. If we want to reduce the size of the transmitted messages in each round, we could try to reduce the actual size of the data that we use for sending the model updates by sampling the model updates or by quantizing the actual updates. We could also try to reduce the number of the size of transmitted messages by having a decentralized organization of the topology in federated learning. And we could use our previously mentioned idea of randomly selecting only a subset of the devices. So the smaller the subset, the less data that we're sending to in each round to the federated learning server. So the idea here is that if we are able to dramatically reduce the number of devices that we select in each round, then we are able to dramatically reduce the amount of work that we have to do communicating with the server. However, that leads to our challenge number 2, which is the statistical heterogeneity with non-IID data. And traditionally, if we upload all of the data to the cloud and do the work in the cloud, do the machine learning training workload in the cloud, the algorithms are typically assuming that the training data is independent and identically distributed, IID. However, if we actually do federated learning on the local devices, then we are reusing all of the algorithms, but just offloading the algorithms to the devices. But it turns out that because that each device only has its local data for training, the data is inherently biased and non-IID. So what we have here is that we have the difference between, on the left-hand side, the centralized way of doing the training where we have the global data, and on the right-hand side, the local training, which is inherent in federated learning, where we have non-IID and biased local data that we use to train our models. And then we try to do this federated averaging in the cloud to combine the result of the training. So what we have here is that we have the problem that the fewer devices that we randomly select in each communication round, which is for the sake of reducing the communication overhead, the more severe the problem it is for the non-ID data that introduces bias into the training and potentially leads to slower convergence. Now, to try to see what kind of a problem it might be, we don't want to trust the papers. So we wanted to just run our own experiments and write our own code. So what we did, we take the kind of the benchmark MNIST data set, and we try to run in our own emulated environment, developed using Python, over multiple communication rounds, and we compare federated averaging with the global data that is IID guaranteed, and federated averaging with local data that is non-IID. So with federated averaging with IID data, it's going to converge quite quickly within about 30, 40 rounds. However, if you actually work on non-ID data, the number of rounds is going to be over 150. So it's going to be much slower to converge. So now the question is, how can we actually fix this particular problem. Now, can we actually try to build the training data so that they're actually IID? No, that is not possible because that is against the design principle of federated learning, where we want to keep the data locally because they're private data. So we don't want to upload the data to the cloud. So we don't have any access to the data on the phone. We can only work with local data. So one example solution in the literature, in the paper that is published in 2018, is to say we're going to have some shared data and we're going to make sure that shared data is IID. And then we're going to just try to download the shared data from the cloud. And then we're going to try to do the training locally by using both the shared data, which is guaranteed to be IID, and the private data that is generated locally. Now, to do something like this, it's going to be incurring two problems. Number one, how do we really get the shared data? If we assume that all of the data would be generated locally and they're actually all private. Number two, it actually increases even more communication overhead for downloading the shared data to the mobile device. Now, if you recall, the whole idea of randomly selecting the devices, a small subset of the devices, is to reduce the communication overhead to the federated learning server. So today, I would like to briefly talk about some of the ideas that we have recently to apply deep reinforcement learning in our experimental testbed to see how do we actually try to reduce the negative effects of using non-ID data to train the model in federated learning. Our paper is going to be published next month in InfoComm. It's titled Optimizing Federated Learning on Non-ID Data with Reinforcement Learning. And since we cannot build global data, what we propose to do is to look into the data distribution on each device without violating any data privacy. And then we're going to hopefully probe for the bias of non-ID data. So what we have here is that we want to carefully select the devices rather than randomly selecting them to balance the bias that is introduced by the non-ID data. So here's a kind of an example of probing the data distribution. Let's say we have 100 devices, and each one of them had 600 samples, say from the MNIST data that we have previously shown. The non-ID data is going to be generated in our, for example, experimental testbed in the following way. We have 80% of the data having the same label, for example, 6, which is out of the 10 digits that we have in the data set. And the other 20% will be randomly drawn from the rest of the labels that we have in the data set. And then we're going to apply the standard two-tier CNN model with around 400,000 parameters in that particular model. So we're going to run this through our experimental testbed, and we're going to try to see what happens here. Now, we want to apply PCA, which is principal component analysis, to reduce the number of dimensions that we have here from 400,000 dimensions in the model weights to a two-dimensional space so that we can easily see what's going on by plotting a two-dimensional graph. So this is the graph that we can plot. And the x and y axes are the two dimensions. So what we have here is that we have the actual colors representing different labels that we have. For example, this kind of yellowish crosses, pluses, will represent the label 6. And these triangles that are in light green will represent the actual label 2. So as you can see here, very interestingly, when we actually try to plot these in the two-dimensional space after we applied principal component analysis to reduce the number of dimensions, we can see they're sort of clustered. And because of that, there is a kind of interesting and simple idea. And the simple idea here is, can we actually just apply some kind of a very simple clustering algorithm? And that clustering algorithm is going to be used to cluster the devices that we have into different groups. And then when we actually try to select the devices, we can just select a representative or a number of representatives within the same group. So we actually have identified an implicit connection between the mobile weights and the model weights and the data distribution. What we wanted to do is that we want to probe the data distribution and select the devices for the federated learning. So to do that, what we wanted to do is that we don't want to actually try to choose the devices or too many devices within the same group. And since we have that clustering algorithm, we are able to identify which device is within which group. So we want to represent each group with the same number of devices. For example, just one device from each group. So in that case, if we have 10 groups, we will select randomly 10 devices. And that would be something that we can do to actually try to reduce the bias in the data that we have when we actually try to train use the data to train our local models. So in this particular case, what we can do is that we can apply k-center clustering, and we select the same number of representatives within each one of these clusters. And what we can do is that within each group, we can just do random selection, but we select the same number of randomly selected devices within each group. And to do something just as simple as that, just a simple k-center clustering based on the actual model weights that we have, we are able to show a better convergence. It's not close to the kind of the ideal situation where we have perfectly IID data in the global model, but it's better than not using the k-clustering algorithm. Again, this result is obtained from our emulation testbed, and this is something that we can actually get started with. Now, we are able to select the devices for federated learning, but the question is, how do we select devices to speed up the training? As much as we can. So previously, we were able to speed up training by a little bit as compared to not using the k-clustering algorithm, k-center clustering algorithm. But now we want to have the best possible selection of devices. So the question is, can we do better than k-center clustering? Now, it is kind of difficult to select the appropriate devices because the model weights, they're actually affecting the selection of devices. And the model weights, they're actually changing over time. So we want to select the best set of devices every single iteration. We probably need something a little bit better than k-center clustering. And today, we would like to introduce our work experimenting with the use of reinforcement learning, in this case, deep reinforcement learning, to actually do this kind of device selection. So just want to briefly introduce deep reinforcement learning. We have the environment. In this case, the environment would be our federated learning environment, and it will actually send the states to the agent. And the DRL agent is going to perform and generate the actions. And these actions are to be applied in the environment. And then we will have the reward. And the reward will have the feedback, sort of like a feedback channel. And that will help to train the agent so that in the next round, it will be able to generate better actions. Now, we would like to train the agent using this kind of sequence of the state, action, the reward, and the next round, the state, the action, the reward. And that sequence is called typically the episode. So we're going to have a lot of these episodes. Typically, we're going to divide these episodes into batches. And then we will try to train the DRL agent using one of the the standard off-the-shelf deep reinforcement learning training algorithms. We want to maximize the sum of reward, probably by have some smart way of summing them up. In terms of the states is going to include the global weights and the local model weights that we have. And because our model weights, we will have over 400,000, we would like to, again, apply principal component analysis and reduce the number of dimensions. And the reason that we do this is because we will have the need of training quickly as we can. So having too many dimensions is not going to help our training to converge quickly. So that's why we need to reduce the number of dimensions. In terms of the actions, ideally, we would like to select a number of devices from a pool of the total number of devices. For example, select K devices from N devices. However, that is a choose K from N kind of a problem. That's a huge action space. For example, if you want to choose 10 devices from a pool of 100 devices, which is not a very large number, you're going to have an enormous number of possible actions. So what we wanted to do is that we want to reduce that total number by modifying this action space by selecting the top K devices, but only have one device in the RL training when we actually try to train and generate the reward. And now the action space is going to linearly grow with the number of devices that we have. It's not going to be growing, with the pace that we cannot cope with. So with N devices, we're going to have an action space of N. Now, that's something that is good, but how do we actually select the K devices? Well, what we can do is that after the last layer of the DRL agent, which is typically a softmax layer, generates all of the probabilities, which are the scores for each one of these actions that we have. We, rather than using the the random sampling and try to generate the actual action that we take, what we can do is that we can simply modify that and we just take the top K based on the actual scores. In terms of the reward function, we want to just have a very simple reward function by having the reward function so that it is going to be increasing when the training accuracy increases as it approaches the target accuracy. So if we actually have a higher training accuracy, we're going to have a higher reward, which is intuitive. Now, we will also would like to reduce the sum of rewards when we have more communication rounds. So it will penalize having too many communication rounds to converge. So that's something that is also intuitive as well. Now, what we wanted to do is that we want to train the DRL agent using a standard off-the-shelf DRL training algorithm. And that is using a standard cumulative return by using a discount factor to discount future rewards. And that's something that we can use to actually try to maximize this kind of sum of discounted cumulated rewards, and then use that as the objective to train the DRL agent. Now, again, we're going to feed the state into the agent, and the agent is going to try to apply principal component analysis, extract the features. Going to feed into the DRL agent's deep learning network, which is the DDQN that we have selected. And then we will go through the softmax, and it will generate the actual probabilities. And we're going to select the top K scores to generate the actual actions. We're going to select the devices with the top K scores. So that's something that is kind of like a standard way of applying DRL. So there's nothing really fancy here. There are no changes in terms of the how do we train the DRL agent, and or how do we actually try to design our reward function. Now, by doing something as standard as this, what we're able to do is we're able to actually see that the DRL agent can be trained. It actually can converge. It takes about 160, 170 episodes. Initially, it doesn't converge, but it's trying to explore itself. And then after a certain number of episodes, it will start to converge. So once it converged, what we can do is that we can take that DRL agent and we can actually try to apply that to our entire federated learning process. The DRL agent will be used to process the model updates and try to do the actual selection of the K devices that we have. So this replaces the K-center clustering that we previously have, and it will try to select the top K devices with the highest probabilities. Once these devices are selected, they will again report their weight updates to the DRL agent again, and the DRL agent is going to use the new set of states. It's going to try to generate the new actions again. To evaluate our solution, we'd like to apply 3 basic benchmarks, machine learning workloads, MNIST, Fashion MNIST, and CFAR10. And we'd like to have 3 different levels of non-ID, half and half, which means that half of the labels are from one, half of the data is from one label and the other half from a different label. 80%, 20%, that means 80% would be from one label, 20% would be generated randomly from all of the other labels, and then 50%, 50%, which means 50% from one label and the other 50% randomly selected from the other labels. So once we are able to, kind of apply this kind of a way of generating the data in a non-ID way, we're able to compare the 3 candidates: federated averaging, with just random selection, K-center clustering, and our own work, which we call favor, that actually uses DRL. For all of these cases, half and half, 80%, 20%, and 50%, 50%. K-center may not beat federated averaging, but favor is always going to be better than K-center, and it is no worse than federated averaging with random selection. So typically, it is able to improve by quite a bit. So these results are generated from our own experimental testbed that we have written from scratch to actually try to evaluate the idea of using DRL to select the devices. So just to summarize what we have talked about, we have proposed a DRL-based device selection process. And again, we want to replace the random selection. We still want to select the K devices randomly, rather than randomly selecting them, we would use DRL to actually try to do the selection. And by just doing something as simple as that, we are able to reduce the number of communication rounds by up to about 50% on MNIST, 23% on the Fashion MNIST, and 42% on the Cipher 10. Now, what we wanted to do is that rather than just writing a paper about it, we would like to contribute towards better reproducibility of the results by open sourcing the actual work that we have done to emulate all of the actual federated learning framework and also our own DRL-based device selection algorithm. So this is available on GitHub, and that concludes what I would like to talk about today. So for more information, just search my name, Baochun, and that will be able to lead you to the actual papers that you can download. And for this paper, you're also welcome to attend InfoComm, which will be next month. Thank you.